In this section, we are going to understand about periodic signals. So let us begin by considering a continuous time signal given by x of t. Now we are assuming a positive value, some positive for some positive value of time capital T, meaning let's say after some time, after time t is equals to t, if x of t plus capital T. So this is the signal, or this is the function after some time t has elapsed. If this gives back our original signal x of t, then we say that x of t is periodic in nature. In other words, what we have done here is by adding the positive value capital T to to the time t, or what we have done a time shift here, and regardless of this time shift, the periodic signal is unchanged by it. So let us understand it with the help of an example. So let us consider a continuous time signal given by this particular graph. So for this particular signal to be periodic, so it should repeat after every t interval. So that means, so we take the signal, copy it, and exactly after a time period of t, this is going to repeat itself. Then we take another copy, it is going to repeat after another t interval. So here we see that the signal, the continuous time signal x of t, is repeating after every t interval. So we could do that on the negative axis as well. So this is an example of a signal, of a continuous time signal which is periodic with a period of t. So this is going to continue in the left hand side as well as in the right hand side. So let's write it down. So here we have x of t is periodic with a period of t. So this is an example of a periodic signal. Now we can generalize this. So generalize this in the sense that if xt is periodic with a period of t, then we can say that x of t must be equals to x of t plus m times t. So this is going to hold true for any value of our time t and any integer value of m. So that means if we consider m is equals to 1, that gives us m t will be simply equals to 1 times t, which is t, and this t is referred to as the fundamental period. This is the fundamental. So fundamental period means a function that is going to repeat on intervals of length t naught. A fundamental period can also be referred to as the smallest positive value of the time t, capital T, such that the equation x of t plus t equals to x of t holds. So let's talk about some more things about the periodicity of a signal. So this definition of the fundamental period is not going to work if our xt is a constant value. Suppose our continuous time signal is a constant value. Let's say its value is 1 for all t. So that means this graph would look something like so we have x of t on the y-axis and time t on the x-axis, and it has a value, the function or the signal has a value of 1. So this is a constant function with a value of 1. So this function is not said to be periodic, although here we can say that x of t plus t is also equals to 1. So this is 0. Let's say after a time period of t, we see that the function has the value of 1. After a period of 2t, it's again having a value of 1. So x of t plus 2t is also equals to 1, even though this function is satisfying the condition that x of t plus t is equals to x of t whose value is equals to 1. Although this is true, but x of t is equals to 1. This is a constant function, so let's write it down. This is a constant function is not periodic in nature. The reason being, the fundamental period of this particular constant signal is undefined, because it is assuming the same value for any choice of t that we make. So regardless of the choice of t, be it at minus t or plus 2t or plus 7t, it's always having the same value. So we are unable to value a smallest positive value of t for which this definition holds. So therefore a constant function is not regarded as a periodic function, even though it satisfies the condition that x of t plus t is equals to x of t. So all other functions, so this is just a function which is a special case which is not periodic. Any function or any signal, let's call it function or a signal, where x of t is not equals to x of t plus t are aperiodic or non-periodic signals. We call it aperiodic in nature. Now let us try to understand a little bit more about the fundamental period t. The fundamental period t is used to define the duration of one complete cycle of the signal x of t. So this is how we define the fundamental period t. The reciprocal of this fundamental period is referred to as the fundamental frequency. So the fundamental frequency, so we're going to represent it by a subscript 0. So this will be referred to as the fundamental period. All other t without the subscript 0 will be the regular period or the multiple of the fundamental period. So f of 0, which will be the fundamental frequency, is defined as the reciprocal of the fundamental period t naught. So this describes the frequency, or how frequently the periodic signal x of t is going to repeat itself. So this is measured in hertz, or cycles per second. For there will be certain functions which are circular in nature. For example, if we have x of t given by the sinusoidal function sine t, so this is a circular function, and to measure the period of this we need the information which will be the angular frequency. So angular frequency is denoted by the symbol omega. There's a Greek letter omega. So it's defined as omega is the 2 pi times the frequency f. So if we are to find out the fundamental angular frequency, so that will be simply equals to 2 pi f naught, which in turn will be equals to 2 pi divided by the fundamental period t naught. So it is measured in radians per second. So in general, a circular function is of the form x of t is equals to a sine omega t plus phi. So this is the angular frequency part. So if we are to consider the the function x of t given by sine of t, its angular frequency omega will be equals to 1. So far we have discussed about periodicity of a signal which is continuous in time. So we can talk the analogous part of the continuous time signal, which will be a discrete time signal. So let us consider a discrete time signal given by x of n. So this discrete time signal x of n is said to be periodic if it satisfies the condition that it is also equals to x of n plus n for all integer values of n. Meaning we can say that x of n is going to be equals to x of n plus n, which is equals to x of n plus 2n, which will be equals to x of n plus 3n, and so on. And also on the left hand side we can have x of n minus n equals to x of n minus of 2n. Like in the case of a continuous time signal, we can also define the fundamental period of a discrete time signal. So the fundamental period will be given by n naught. So this will be the fundamental period. So this will be the smallest integer value of n naught for which this equation holds. So once we know the fundamental period, we can also define the fundamental frequency, which will be the reciprocal of the fundamental period n naught, and it will be measured in hertz or samples per second. And we have the angular frequency. So the angular frequency is given by omega naught, which is equals to 2 pi n divided by n naught for n belonging to integer values. And this is going to be measured in radians. The difference between the angular frequency for a continuous time signal and a discrete time signal is that this value 2 pi n naught must always be an integer. That means this must always be an integer value. So it is defined for all integer values only. So for that we have to pick up the value of small n very specifically such that this fraction reduces to an integer. We'll do more numericals. So let us start with a discrete time signal. So here we have a discrete time signal given by x of n is equals to cosine of 2n. So first we have to check whether the given signal is periodic or not. If it is periodic, then we'll have to determine its period. So let us begin. So there are two ways of computing the period of this particular signal. So we'll start with the first one. So for this particular signal to be periodic, then x of n, will first find out the value of x of n plus n. So that will be equals to cosine of 2 times, so we're replacing small n by n plus n. So that gives us cosine of 2n plus 2n. So we know that for x of n to be periodic, this 2 of n must be equals to a multiple of 2 pi, where m is an integer, because 2 pi is the period of a cosine function. So from here we get n is equals to 2 pi, it's the 2 and 2 cancels out, so we have pi m. Now we have to select some special value of m such that this product pi of m becomes an integer, but there is no such value of m which will make this n into a integer. So there does not exist any integer m, an integer value of m for which the period n will be an integer. And for this specific reason we say that x of n is not a periodic signal or a periodic function. So this is the way we do. This is our method number 1. So let's do method number 2. So method number 2 we'll talk in terms of the angular frequency. So we have x of n equals to cosine of 2n. So comparing with the standard form of a cosine function, which looks something like a cos of omega n, we get the omega value equals to 2. So now that we know the value of omega, so n value will be equals to 2 pi m divided by omega, where m is an integer. Now we see that okay, so let's replace the value of omega by 2, so that leaves us with pi times m. So we use the same logic, so no value of m is going to make this an integer value, so we'll say does not belong to the set of integers for any values of m. Therefore x of n is aperiodic in nature. Let us do another problem. So here we have another discrete time signal given by cosine of 2 of pi n. So we have to first check if this given signal is periodic in nature or not, and if it's yes, then we will try to find out its periodicity or the fundamental period. So let us begin by finding out the value of x n plus capital N. So that will be equals to cosine of 2 pi small n plus capital N, and that gives us cosine of 2 pi n plus 2 pi capital N. So for this, for x of n plus n to be periodic in nature, we have 2 pi of n must be equals to some integer multiple of 2 pi m, where m is an integer. So solving for n, we get n equals to m, and the smallest integer value, in order to find out the fundamental frequency, so this equation must be true for the smallest integer value. The smallest integer value possible for n to be the fundamental frequency, to be the fundamental period, is m equals to 1. So that gives us n, the fundamental period, is equals to 1, which implies that the fundamental frequency f naught is equals to, so this will be n naught, so 1 over n naught is equals to 1 over n, which is 1. So we have the fundamental frequency is 1 sample per second. So this is a periodic function which has having a period of 1. So here we have now the discrete time signal given by sine of 6 pi n over 7 plus 1. So we first check whether this given signal is periodic in nature or not. So we are going to do we are going to use method number 2. So comparing x of n with the general form, x of n is equals to a sine omega n omega n plus some integer m. We get the value of omega equals to 6 pi over 7. So this is the value of the angular frequency. Now we'll try to find out the value of the period. So the period is given by n equals to 2 pi m over omega, where m is some integer value. So substituting the value for omega, so we have 6 pi over 7, so we have 7 multiplied to the fraction. So 2 and 6 will get cancelled out, so that will give us pi m, 7 pi m over 3, so the pi also gets cancelled out, so the final value will be 7m over 3. So here also we see okay, since the pi gets cancelled out, so now we have to select some specific value of m such that n becomes an integer. So for m equals to 3, we obtain the lowest integer value of n. So we'll get n is equals to 7 multiplied by 3 divided by 3. So that gives us an integer value of 7. So this will become our fundamental period. So the fundamental period of the given discrete time signal is 7. So we say that x of n is a periodic function with fundamental period n naught is equals to 7. So here we have a discrete time signal x of n given by cosine of n over 8 minus pi. So let us first check whether the given function is periodic or not. So we'll find out x of n plus capital N, and that will be equals to cosine of 1 over 8. N will now get replaced by n plus n minus pi, which is equals to cosine 1 over 8 n plus 1 over 8 n minus pi. We're going to rearrange the argument. So we have 1 over 8n minus pi plus 1 over 8n. So for x of n to be periodic in nature, this value 1 over 8 times n must be some integer multiple of 2 pi m, where m is some integer. Now solving for n, we get 8 times 2 is 16 pi m. There is no such value of m. No integer value of m exists for which n is an integer. Therefore, the given signal x of n is non-periodic or aperiodic in nature. Non-periodic. Let us go to the next problem where we'll be dealing with continuous time signal. So here we have a continuous time signal x of t given by 3 times the cosine of 4t plus pi over 3. So we have to check whether the given function is periodic, and if yes, then we'll try to find out its fundamental period. So let us begin by comparing it, the general form, comparing with the general form given by x of t equals to a cosine of omega t plus phi. We get omega equals to 4. So definition of omega is 2 pi over t, which is equals to 4, and that gives us the value of t is equals to 4 over it's 2 pi over 4, which is equals to pi over 2. However, there is no problem while finding out the period of a continuous time signal, because it can assume any value. T can assume any real value, so we do not have to worry about finding an integer value. So here the period, it's a periodic in nature. So a cosine function is always periodic. So this particular cosine function has a period of pi over 2. So its fundamental period t naught will be equals to pi over 2, which will be radians per second. Let us do another problem. So here we have another continuous time signal given by x of t equals to cosine square of 2 pi t. Now we have a squared cosine function, so we will need to use some trigonometry. So we're going to apply the identity that cosine square theta is equals to 1 plus cosine of 2 theta divided by 2. So when you apply this, so we'll get cosine square of 2 pi t will have the form 1 plus cosine of 2 times 2 pi t will give us 4 pi t over 2. Then we can rewrite it as half plus half of cosine of 4 pi t. So this is the reduced or the simplified form of our continuous time signal x of t. Now we'll have to find out the period of this particular signal. Now when we find out the signal, so we don't have to worry about the constant part, that is half. We only have to look for the trigonometric function here. So here when we compare with cosine of omega t plus phi, so here we have the omega value is equals to 4 pi. So that means the period will be equals to 2 pi over omega, which is equals to 2 pi over 4 pi, and that gives us half. So this is 0.5. So we can it's radians per second. So this is measured in radians per second. So this is going to be the period of this continuous time signal given by cosine square of 2 pi t. Let us do another problem. So this is quite similar to the previous problem. Here also we have a squared cosine function. So let us first reduce it to a simplified form. So we apply the same formula. So we have x of t will be equals to 1 plus cosine of 2 times 2t minus pi over 3 divided by 2, which gives us half plus half cosine of 4t minus 2 pi over 3. So comparing with cosine omega t, we have omega equals to 4, so that gives us t value, which can be computed by using the formula 2 pi over omega. So we have 2 pi over 4, which gives us pi over 2, and it's measured in radians per second. So this is going to be the period of this particular function. So here we have a continuous time signal x of t given by sine cube of 2t. So we have to simplify sine cube. This is a cubic function, cubic trigonometric function. So we have to get rid of the cubed value here. So here we are going to use the identity that sine 3t is given by 3 sine t minus 4 sine cube t. So when we solve for sine cube t, so that gives us sine cube t is equals to 1 by 4 multiplied by 3 sine t minus sine 3t. So we're going to use this particular formula, but we have sine cube 2t. So that means x of t will be equals to 1/4 of 3. So instead of sine t, we'll rewrite it as sine 2t minus sine 3t. So t will become 2t. So 3 times 2 will gives us 6t. So the reduced or the simplified form of x of t will be 3/4 of sine 2t minus 1/4 of sine 6t. So this is a simplified form of a time signal, the continuous time signal. Now we are going to assume that this x of t is composed of two signal x1 of t. So that x1 of t is 3/4 of sine 2t plus x2t. So x2t is the second term in the signal x of t. So this okay, let's find out the period of each of the two functions x1 and x2 independently. So we begin with x1 of t. So x1 of t is equals to 3/4 of sine 2t. So here, when we compare it to our standard form, we get the omega value. So we'll consider it as omega 1 is equals to 2. So this gives us the time period t1, which is 2 pi over omega 1. So we have 2 pi over omega, which is 2. So that gives us a period of pi. Then we consider the second function, x of 2t, which is equals to negative 1/4 of sine 6t. So we are going to compare with the standard form, and that gives us the omega value 6. So we get a period of t2 is equals to 2 pi over 6, which is equals to pi over 3. So now we have two periods. The first part of the signal, which is x1t, has a period of pi, and the second part of the signal x2t has a period of pi over 3. So in order to find out the combined period of x of t, we need to determine the lowest common multiple of both the two periods. So that means the period of x of t is equals to the lowest common multiple of pi and pi over 3. Now, how do we determine the lowest common multiple of pi and pi over 3? So the trick that I'm going to use here is, so we consider the first one, the pi. We're going to multiply both the numerator. We're going to multiply it and divide by 3. We are doing it specifically so that it has a denominator which is exactly equals to the denominator of the second period, which is pi over 3. So now that it has a common denominator, all we have to do is find the lowest common multiple of 3 pi and pi, and whatever be the answer, we are going to divide it by the common denominator, which is 3. So the LCM of 3 pi and pi is 3 pi, so we have to divide it by 3. So that gives us a combined period of pi. So this is the period of the function x of t. So let's write it down with a different color. So therefore the fundamental period of x of t given by sine cube 2t is pi. So this is how we find out the period, the fundamental period of a continuous time signal. So in this question we have x of t, which is a continuous time signal, that is equals to 2 times the cosine of 10t plus 1 minus of sine 4t minus 1. So we are going to suppose that the first trigonometric function is given by x1t plus the second trigonometric function is given by x2 of t. So we'll try to find out the period of each of them individually. So for x1t given by 2 cosine of 10t plus 1, here comparing it with our standard form a equals omega t plus phi, we have omega 1 is equals to 10. So that gives us the fundamental period, which is t1 is equals to 2 pi over omega 1, which will be equals to 2 pi over 10, and that gives us a period of pi over 5. So this is going to be the fundamental period of x1t. Similarly, we're going to find out the period of x2t, and x2t is given by negative sine 4t plus 1. So here omega 2 value is equals to 4, so that gives us t2 equals to 2 pi over omega 2, which is 4. So we have a period of pi over 2. Now in order to find out the period of xt, so the period of xt will be equals to the lowest common multiple of x1 and x2. So that is, we have to find out the lowest common multiple of pi over 5 and pi over 2. So in order to find out the lowest common multiple of two fractions, what we do first, we find out the lowest common multiple of the denominator, which is 5 and 2. So the lowest common multiple of 5 and 2 will be 10. Now what we're going to do, we are going to we're going to convert each of the fraction in such a way, we're going to write this such a way that they have the same common denominator of 10. So we multiply and divide the first fraction pi over 5 by 2. So that gives us 2 pi over 10. And the second fraction pi over 2, we multiply the numerator by 5 and divide it by 5. So that gives us 5 pi over 10. So now that we have a common denominator of 10, so this will be equals to the LCM of only the numerator, which is 2 pi and 5 pi. And whatever be the answer, we're going to divide it by 10. So the LCM of 2 pi and 3 pi is going to be 10 pi. It's very obvious. And divided by the common denominator, which is 10. So that gives us a fundamental period of pi. So here in this question, we have a discrete time signal x of n given by the product of two cosine function with the argument pi over 2n and pi over 4n. So first we have to do some trigonometric manipulation here. So we are going to use an identity that the product of two cosine function cos of a and cos of b can be rewritten as the sum of cosine a plus b plus cosine of a minus b. So we're going to use this identity. So our x of n becomes half cosine of pi over 2n plus pi over 4n plus cosine of pi over 2 times n minus pi over 4 times n. So this becomes equals to half cosine of this becomes 3 pi over 4 times n plus cosine of pi over 4 times n. Or we can say this is equivalent to half of cosine 3 pi over 4 times n plus half of cosine pi over 4 times n. So this is our discrete time signal x of n. Now we have decomposed the product into two sums. So let us assume that the first term is denoted by x1 of n and the second term is denoted by x2 of n. So this is our discrete time signal. Now we're going to find out the period of x1 and x2 independently. So we have x1 of n given by half cosine of 3 pi over 4 times n. So here, when we compare it with our general form, we have omega naught equals to 3 pi over 4. So with this we can find out the fundamental frequency, but this will be the general frequency. So this is also the general omega value, not the fundamental one yet. So T will be given by 2 pi m, where m is some integer, divided by the angular frequency. So we have 2 pi m divided by omega. Omega value is 3 pi over 4, so 4 gets multiplied. So we can cancel out pi from both the numerator and the denominator. So this becomes, so our t value is now equals to 8m over 3. Now, there's one mistake I have made, not exactly a mistake. So since we are in the discrete time domain, so this will be simply denoted by n1 instead of t1. So our n1 value is equals to 8m over 3. Now since we are trying to find out the fundamental frequency, the fundamental period, so we must have a smallest integer value of m, so that this n1 becomes a integer. So for m equals to 3, n1, this is the smallest value of m, for which n1 becomes equals to an integer. So we have 8 times 3 divided by 3, so that gives us 8. So it has a period of 8. Now we come to the second signal, which is x2 of n, and that is given by half cosine of 4 simply pi over 4 times n. So here we have the angular frequency equals to pi over 4. So we can find out the period. So the period n2 will be given by 2 pi. Now let's consider a different integer value p divided by omega. So this is omega 2. The previous one was omega 1. So divided by omega 2. So we have 2 pi p divided by omega 2, which is pi over 4. So we multiply by 4. So the pi and pi will get cancelled out. So this gives us 8p. Now we consider the smallest integer value for p, which will be equals to 1, such that our fundamental period n2 becomes equals to 8. So now that we have the period for each, so the fundamental period of original discrete time signal x of n will be simply equals to the LCM of the lowest common multiple of n1 and n2, which is equals to LCM of n1, which is 8, and n2, which is also 8. So that gives us a period of 8. So this will be the fundamental period of the discrete time signal. So here we have a discrete time signal that is composed of 3 trigonometric functions. Now we consider the first one to be x1 of n, the second one to be x2 of n, and the third one to be x3 of n. So this will be x of n, and we'll try to find out the period of each of x1, x2 and x3. So let us begin with x1. So for the signal x1 of n to be periodic, so we'll consider the angular frequency omega 1. So the omega 1 is equals to pi over 4. So using this we can find out the period. So the period n1 is equals to 2 pi over omega 1. So that gives us 2 pi over 4. So we multiply by 4. So that gives us a period of 8. Then we come to, this is 2 pi, I made a mistake, 2 pi n is there. So we have 8 of n. So the smallest integer value m can have is of m will be 1, so that we get the fundamental frequency, the fundamental period n1, which is equals to 8. Now we find out the fundamental period of our second signal. So for x2 to be periodic, so we have omega 2 value is equals to pi over 8. So that gives us n1 equals to 2 pi, since we have already considered n, so let us consider p. So 2 pi p over omega 2, which is pi over 8. So pi and pi gets cancelled, so we have 16p. So this will be equals to 16 when the smallest value of p is equals to 1. Similarly, for the third signal x3 of n, we have omega 3 is equals to pi over 2. So this is n2. So we have n3 equals to 2 pi, let's take r, divided by pi over 2, which is equals to 4r, and this will be equals to 4 when the smallest integer value of r is equals to 1. So we have the period of each of the discrete time signal x1, x2 and x3. Now let us combine them so that we can get the overall period of x of n. So the period of our given function, discrete time signal function x of n, will be simply equals to the LCM, the lowest common multiple of the period of x1n, the period of x2 and the period of x3. So that will be equivalent to the LCM of 8, 16 and 4. So the LCM of 8, 16 and 4 is equals to 16. So this is going to be the overall period of our discrete time signal. So here we have a discrete time signal x of n given by the cosine of pi over 8 times n squared. So in order for the discrete time signal to be periodic, we'll first find out the value of x of n plus capital N, and this should be exactly equals to x of n. So we have cosine of pi over 8 multiplied by n gets replaced by small n plus capital N squared, which will be equals to cosine of pi over 8 multiplied by n squared plus 2 small n times capital N plus n squared, which is equals to cosine of pi over 8 n squared plus pi over 8 times 2nn plus n squared. So this is the value of x of n plus n. Now we know that for this particular discrete time signal n plus n to be periodic, this value must be equals to pi over 8, 2nn plus n squared must be equals to some integer multiple of 2 pi. Let's call it m. Right, m is an integer. So that gives us 2nn plus n squared is equals to 16m. So clearly we see that the left hand side of the equation 2nn plus n squared is a multiple of 16 for all values of, this is true for all values of 10. So for simplicity purpose, let us consider the most simplest value, n equals to 0. So that will give us n squared is equals to 16m. Now what must be the smallest value of m so that we get a perfect square? So this means for m equals to 4, this gives us n squared is equals to 64, which gives us the value of n is equals to 8. So this will be the fundamental period. We can even check out for a different value of n. So let's take n equals to 1. So that gives us n squared plus 2n is equals to 16m. Now for the value of m, this particular value is going to be valid. So the smallest value of m. So let us consider the smallest value of m equals to 5. So if m is equals to 5, this will be the smallest integer value possible. So that gives us n squared plus 2n equals to 16 times 5, which is equals to 80. So we have n squared plus 2n minus 80 is equals to 0. So factorizing this equation, so we have n squared plus 10 times 8 is 80. So we have 10n minus 8n minus of 80. So that gives us n of n plus 10 minus, factoring out 8 from the third and the fourth term, we have n plus 10 equals to 0. So that gives us n plus 10 times n minus 8 is equals to 0. So we can have either n plus 10 is equals to 0 or n minus 8 is equals to 0. So this is not going to be possible because n cannot be negative. This is the period we are talking about. So that gives us n is equals to 8. So both the cases we are getting the period, the fundamental period is equals to is equals to 8. Since we are able to calculate its fundamental period, so that means the discrete time signal x of n given by cosine of pi n square over 8 is a periodic signal.